to something more interesting and talk about the Bayes theorem, right? So the Bayes theorem is named after this guy. It's called Reverend Thomas Bay. Or is it Bayes? I don't know. Yeah, but then it's named after this guy. And then the major idea behind this work, though he didn't publish it, he died before they named the Bayes theorem after him. But then it was found in some of his unpublished work. Now the idea was that if we have the probability of something happening, okay. So let's say the probability of me. So let's say me going to class today is going to class is say 1 on what? Let's say 1 on 2. Okay. So the probability of me going to class today is 1 on 2. Now I'm sitting there and I get new information that there's going to be a quiz. So if there is going to be a quiz, will that change this probability? Yes. So that's just the idea that if you have new information, right? If you have new information, then the probability changes. So the probability of something happening with new information changes. Okay. So yeah, so that's basically the major idea behind the Bayes theorem. And then when we're working with Bayes theorem, we are trying to find the effect of some new information on how something will be done. So probably this my hypothetical probability of going to class 50%. If there's a quiz, then it can either just jump up to 1 or maybe something like 90%. Always the same as 0.9 anyway. Yeah, so that's just the idea behind um, the Bayes theorem. Okay, so let's get more to it and then see what it really entails. Now let's just re-establish the formula we had. So that's the probability of A given B is the probability of A intersection B all on probability of B. Now they can write this thing in different forms. You can find them. So you can find like probability of A intersection B equals probability of B times probability of A given B. Yeah, so they can write it in different forms and it's still fine. Now, when do we apply the Bayes theorem? So when do we apply the Bayes theorem? Okay. Okay, so most of the time when you are considering to use partition your sample space into some mutually exclusive events. So let me see when to use. Then use when you are doing with mutually exclusive. So what are mutually exclusive events? Mutually exclusive events are like so let's just say they are independent on each other, right? So the occurrence of one does not depend on the other. That's mutually exclusive. So and you can have a set of them. You can have A1, A2 to some AN. Okay. So probably I'm just trying to evaluate the probability of one of the mutually exclusive events given some new information. Okay. Yes. So maybe in the analogy up here, so if we have some two events like one, maybe A1 is me going to class, and then maybe A2 is me going out somewhere else. Then yes, so you can just classify them as mutually exclusive events if they don't fully depend on each other. Like if they don't depend on each other at all, that's when you can start using the Bayes theorem. And most of the examples we'll meet, they don't depend on each other. Now with Bayes theorem, we have some prior knowledge, right? So prior knowledge is what do you know? Prior knowledge. Prior knowledge, right? Prior knowledge is what do you know? We know this. What is the new information? Or maybe what can be the new information? So the combination can be the new information. So what's the probability of A intersection B? That can probably be some new information. Not necessarily only the probability of A. Okay. So this obviously comes into the new information you get. Then when you solve Bayes theorem, you mostly land at things we call the posterior probabilities. And as the name implies, So just like projecting into what can happen or what would have happened, stuff like that. So that's posterior probabilities. So we would consider some major things in the slides. Okay, so let's pick some example. Okay, so we'll just solve one example and then we'll go to solving some. So we'll solve, let me say, 3 examples from this lecture. So let's pick one. So one is that we are going to pick some suppliers. Okay. Um, so let's say supplier one, supplier two, and then okay. But anyway, let's continue. And then so we have good, bad. So let's say the supply goes to your company, and then the probability of supplier one giving you like good goods is 0.9, and then the probability that they give you bad goods is 0.02. The probability that supplier 2 gives you, or what should I call it? Okay, so instead of goods, let's call it like good items, right? So good items 0.95, and then bad items will be 0.05, right? So this will be what we are going to work with. Now you want to find. Okay, so this one you can draw a tree diagram, which makes it easier to analyze. So in the first place, what's the probability that whatever you are buying from, say, supplier one, right? Okay, but then you see, with this one, we're not told, okay, if you are buying from supplier one, this is the percentage. Okay, so I think I didn't finish. So you need some more information to finish up this diagram. Then I'll show you that in a moment. Okay, so then so you have two suppliers, right? You can call the supplier one, supplier two. But what is the probability that you even buy from any supplier at all? So let's say that in the slide we assume that the probability of buying from supplier one, right, is 0.65, which makes the probability of buying from the second supplier being 0.35. Okay, that's cool. So now, if we take supplier 1, what's the probability that gives us good items? That's 0.98. So this is good. And probability that gives you bad items will be 0.02. So this is bad. Now this is good. This is 0.95, like we stated, and 0.05 bad. Okay, so now this is our baseline. This is the baseline. So now let's just try to analyze what we are doing here. So let's call this guy supplier A, supplier B. So now, what is the probability that, so the probability that something, you have good items from supplier 1 is this times this. So it's from, so here it's from supplier 1 and it is good. It's from supplier 1 and it's bad. From supplier 2 and it's good. From supplier 2 and it's bad. Okay, so that's the baseline. So now that we've set the baseline, let's try and do some small manipulations on this. So now let's say we want to find the okay, so this is what I was trying to explain earlier too. So if they ask you to find the probability that it is good, given that it's from supplier what, given that it's from supplier A, this is not the same thing as is this. These are very these are very different things, right? So probability of the probability that is good given that it's from A. So if it's good given that it's A, then this one you don't really need to calculate, right? It's just this one. I hope you agree with me. Yeah. And then if you want to find the probability that it is, so you know that it's good, but you want to find the probability that it's from supplier A. Now this is where you can start working something. Now, like I demonstrated in the first one, when you try to work this one, the probability of A will just cancel out from the top and down, and you still get the same thing. So now let's solve this. Right. So if you have to solve this, what do we do first? Then first you have to find your probability that it is good. Right. probability that is good. So what's the probability that is good? It's good if it's from A and it's good, or it's good if it's from B and it's good. So this is your good line, your good line, right? Something like this. So here that will be 0.65 times 0.98 plus 0.35 times 0.95. So this is it, right? And you can punch this into your calculator. Let me see, 0.65 times 0.98 plus 0.35 times 0.95. Okay, hope it's not wrong. But then yes, so the probability that is good is 0.9695. Good. Now with this probability, right, now you would like to find the probability that is from A if it's good. Then that gives you probability of A intersection good all over probability of good. Now what's the probability of A intersection good? Right? So probability of A intersection good is A good. So that's what, 0.65 times 0.98. Then you divide all of this by your 0. This one, probability that is good, 0.9695. So I can just say answer. Then I say 0.65 times 0.98, and then this gives us 0.65. So let's just leave the 0. Okay, so 0.657. So from this one, right, it tells us that if you have some good item in your shop, then the probability that it is from supplier 1 is 0. Or let's say 66%. Right, 66% that if it's good is from supplier 1, because which makes sense, because supplier 1 supplies 65% of your items, and then on top of that he supplies at a very high quality. Yeah, so that's one way to solve. Now let's say you are trying to find the probability that is bad. So let's try this one too. So what's the probability that it is okay, is, so given that it is bad, what's the probability that from supplier A? Okay, now something like this. So if we try to solve something like this, then first we have to find probability of bad. So how do we do that? So probability of bad will be, so it's from A and it's bad, or it's from B and it's bad, right? So let's just calculate that. So we'll write that again. So that'll be 0.65 times 0.02 plus 0.35 times 0.05. So the probability that is bad at all is 0.0305. Okay, so 3% of your goods will be bad. Now, what's the probability that is from A and it's bad? Now we know that A delivers very high quality goods, so then we should be expecting something very low. Then that will be 0.65 times 0.02 all divided by 0.0305. Then we can just pick answer. Then we say 0.65 times 0.02. Okay, so yeah. Okay, so the probability that you have goods that are bad and it's from supplier 1 is 0.426. So that means that of all the bad goods you'd have, the probability that is from supplier 1 is 4%, 43%. Okay, 43%. Is that making sense? Yeah, I think so. Because he supplies much of your goods, and then he supplies at so the bad ones are very small. This guy supplies small and then relatively high, so it makes sense for him to have 43%. So yeah, because if he was given a 35%, then you find that he would relatively give lower. So it's making sense. Yeah. So that's just the way to solve conditional probability. That's just the way to solve conditional probability. And then now you find some relations in the slides, and then they might be looking so plenty and messy. Okay, so in the slide you find something like probability of B equals probability of A1 intersection B plus probability of A2 intersection B. In fact, it actually goes on to probability of AN intersection B. Now this is basically saying that the probability of A, right? So that is simply this and this plus this and this. It's just the same thing. Right? It doesn't really change anything. Yeah. So that's just a relation you can always keep. Yeah. And then okay, so that relates to what we said in the first video. So let me see what's next. Okay, so you have some examples in the slides. Right? They all use the same approach used here. All of them use the same approach. So maybe you can try the car example. Someone getting to work late because the answers are there. So and then the next one is the disease control question. It has the same solution. And then okay, we have a question here that doesn't have a solution, but it has an answer. So let's attempt that and see if we get it correct. Okay, so it says when you open your slide, it says try this question on Bayes' theorem. Okay, so let's try. Hopefully we don't get a wrong answer. So it says that suppose a certain drug, right? Certain drug test is 99% accurate. So the drug test is 99% accurate. That is, the test will correctly. So drug test. I'm just 99% accurate. Okay, and then it says that so the test will correctly identify a drug user as testing 99% of the time, and will correctly identify a non-user as testing 99% of the time. Okay, I think that makes sense. So that means that if you are a user, right? If you're a user, it will identify you 99% of the times, and if you're not a user, it will identify 99% of the times. Okay. Now this would seem to be the relatively accurate test, but Bayes' theorem reveals a potential flaw. Now let's assume a corporation decides to test its employees for opium use, and 0.5% of the employees actually use the drug. You want to know the probability that given a positive drug test, an employee is an opium user. This is really an interesting question. So now, and then users is actually 0.5%, right? So every company that 0.5% use the drug. So now let's come here. Then you start from where? You start from your users, because those are the people you're going to be dealing with. So you have 0, so this is 0.5, then level 0.95. Okay, but then please take note of this. This is 0.5%. Okay, so there's 0.995, and then there's 0.05. So please take note of this, because it can render everything, can turn everything into should I say cost 90? Yeah. So from here, then these are the users, right? Let me just say. So these are users. Let me just denote this with users and non-users. Now, if you're a user, it identifies you 99% of the time. And if you're not using, it says that okay, this boy is not using. And then if you're a non-user, so let's say accurate, right? Accurate, not accurate, accurate, not accurate. So if you are not using, it says that okay, yeah, this boy is not using, so that's 0.9. But then someone cannot be using, it says that okay, you are using. I hope you get this idea. So now the question is, we have to find the probability that a given drug test, given a positive drug test. So now okay, now this one, so you can really label them positive. So all of these are positives, right? Okay, so this is positive, this is a positive. So just trying to understand the dynamics, right? Dynamics of this. Okay, so now let's get to it. So we are trying to find the probability that someone is a user, right? given the test set is positive. So now first, what's the probability that is positive? Now the probability that you are positive is you are using and you are positive, or you are not using and you are still positive. That's just it. So that's 0. Okay. I think I turned up something. I don't know if you noticed. So here, so this is the 0.9. So these are not users. Okay. So this is a non-user. So these, because, and then it was a small population that was using it. So sorry for this one, I've corrected it, but then everything else remains the same. So here, so if someone is not using, then it says that, so where will be the positives? This will be your positives, right? So if you are not using, 99% of the time say you're not using, and then this percent of the time to say you're using, so this will tell that yeah, you are using. Okay, so this is not accurate. Now, if you're actually using, the 99% of the time to tell that you're using, so these are positive. Then this one, right? So these are the people it would. So the users, these are the users that will skip the test. So let me just explain everything that's happening here. So what's happening here is that you have 99.5% of the population not using it, but then when they do the test, 99% of the time it's okay, you're not using it. But then for some small population, that's the 0.1, it will say you are actually using it when you're not using it. Now, for the users, 99% of the time to identify that you are using the drug. But then for some few users, it doesn't catch them. So like the drug test does not catch those people who are actually using it. Some few percent of them. So now what's the probability that a drug test is positive? So that's 0.9995 times 0.01 plus 0.05. Is it 0.05 or 0.005? So here, right? It's this is definitely a mathematics issue. So please just take note of this. I've realized I've done this mistake like twice. Yeah, so just take note of this because it's really deadly. So you have 0.05 times so here. So the positives, this will be the positives, not this one. That'll be 0.99. Okay, so now let's calculate this. So 0.995 times 0.01 plus 0.005 times 0.99. Okay, so that is some interesting number. Let's see if we can make sense of it. So this is the probability that someone is positive, right? This is the probability someone is positive. Okay, so for now, okay, let's continue. For now, I don't know if it makes sense or not, but yeah. Okay, but then I think it makes sense, right? Because this tells you that so there's 1.49%. So that means that the drug will test that 1.49% of the time people use the drug. Meanwhile, only 0.5% are using the drug. Right. So this is making sense logically. So that means that though the test is accurate, but then if you have a very small number that is using the drug, the test becomes inaccurate. Now let's see that the probability that someone is a user, right? And then they are testing positive. Right. So this. So what's this? So that's why the user, this is the user testing positive. So that's 0.005 times 0.99. Right? So 0.005 times 0.99. Okay, so this is a relatively small number. Let's keep it as okay. Now, what's our final task? Our final task is to divide this by 0.0. Hope you can see. So this number by 0.0149. Oh, okay. So hopefully we had an answer. So probability of you Ring P equals probability of U intersection P and probability of U of P. Sorry. Now this gives us 0.3322. Good. Yeah. So that's just it. That's just how to solve this kind of stuff. So I hope this was helpful. Let me see if we have another question we can tackle. So yes, you have another question about some bicycle people. It's just the same approach, And then there's a cancer something. It's basically the same approach. And you have some tractors. So yeah, you can always try these things, but they all use the same basic principle. So try to analyze what do we know, what is the new information we have, stuff like that. Okay. Okay. So basically, I was trying to find another example that we can look at together. Yeah. Okay. There's this tractor example, but then the slide, the answer is already in the slide, so it won't be so interesting to solve. So you can check that out too. It's quite straightforward. And then okay, so yeah, so there's a long example about some tractors, and so it's just the same format. Okay. So if you have any comment or anything, you can always put in the comments box. We'll check it out. And for the meantime, maybe we'll solve some of the questions and put in the groups. Okay. So thank you for watching.